Hi students, welcome to Year 9 Science and Unit 1 Atoms and Stuff. This is video number 7 and we're going to be continuing our look at the changes in the development of our atomic model. And this time we're going to focus in on the work of Ernest Rutherford. So don't forget, we're setting this in the context of how our understanding of atomic structure has changed as we've understood more about the internal structure of the atom in terms of protons, neutrons and electrons. So Rutherford was a scientist in the early 20th century. He was originally from New Zealand but did a lot of his work in England, and probably what's most significant about Rutherford's contribution is the experiment that came to be known as his famous gold foil experiment. Now, Rutherford had a suspicion that atoms were actually mostly empty space, and he set up this experiment where he fired alpha particles. Now, alpha particles are actually helium nuclei, so they have some mass, and they also have a positive charge. And what he hoped to show was that the alpha particles would mostly just pass straight through a piece of gold foil. Now, the fact that it's gold foil is one of the reasons why it's hard for us to reproduce this experiment in the laboratory. But his premise was that most of the atom is empty space, and therefore the alpha particles will just pass straight through, and maybe with small amount of deflection. And pretty much most of what happened was exactly what he was expecting. So we had a screen that was set up. Sometimes you'll see this as a curved screen that sits almost 180 degrees around this foil, because he not only found that some of the deviations were minor, a small angle away from directly passing straight through, but he found some were very significant. In fact, to the point where some almost came straight back towards him. The phenomenon was so surprising. You can see sometimes it's apocryphally described as firing a cannon at a piece of tissue paper and having the cannonball bounce back towards you. That kind of gives you an idea of the magnitude of surprise that this experiment created. But what it did was it made Rutherford think about his model of the atom and how we explain not only some particles passing straight through this gold foil, some particles being slightly deflected by the gold foil, but most unusually, the gold foil actually slowing the particles to the point where they can actually reverse the direction from which they're coming and virtually push them back in the direction in which they came. That seems to be very surprising and difficult to explain, certainly with the model that we have. So is there some way that we can modify that model in order to take these observations into account? Well, Rutherford did. His first conclusion was that the atom is mostly empty space. But he did say that at the very center of the atom is a very dense nucleus, and this nucleus contains positively charged protons. So he now has a very strongly charged positive center of the atom, and so therefore if another positively charged particle comes towards it, we know that opposites will attract, but like charges will repel. So what will happen is that this will actually exert a force of repulsion from the nucleus of the atoms in the gold foil to the helium nucleus that's coming towards it, or the alpha particle, and actually repel it to the extent where if it's almost coming directly at it, it will slow it down and actually push it back in the other direction. If it's coming near but not directly, then what it may do is give it a little push, a little repulsive push, that'll actually knock it off its straight line. And of course, if it happens to just pass nice and neatly through the particles, through the gold foil, and it won't be deflected at all. So some of the particles did actually make it to the other side of the detection screen. Now, in order to take into account these little electrons that had already been identified previously by Thomson, he said that we have to, if we're concentrating all the positive charge at the nucleus, we have to distribute the electrons around the outside. And often you'll find Rutherford's atomic model described as a solar system model. So where the sun, if you like, is the nucleus at the very center of the solar system, and then the electrons are planets orbiting the central nucleus. So that gives us a model that looks something like this. So you can see here's Rutherford's model. Here's alpha particles surprisingly bounced back, and he had to explain that observation. So he gave us the nucleus, and he also gave us a positive charge for the nucleus, which was really important. But one very important limitation of this model is what we didn't really understand, why the electrons should just stay in orbit. Why don't they come crashing back into the nucleus at some point? After all, if opposite charges attract one another, surely the negatively charged electrons would be attracted to the positively charged nucleus and lose energy as they go round and round, eventually to bounce back in. Well, that problem needed a quantum solution, and it also needed the brilliance of Niels Bohr to solve it. And that's going to be the subject of our final video. Thanks for watching.